Hello everybody, and welcome back to another quiz tutorial. So in this quiz tutorial, we're going to be covering quiz number 15, which is strain measures. And yes, this is a beefy quiz. So before we begin, I highly recommend you guys grab yourself a drink, maybe grab some snacks, and settle in because yes, this is a long quiz. It's why the video is a little bit late because I need to make sure that you guys really understand this because even though it's a beefy quiz, it's also a very important quiz. Strain measures are one of the keys to continuum mechanics, and if we don't understand strain, well, then the topics after strain, such as stress and things like that, it's going to be really difficult. So it's very, very important that we have a good understanding of strain in three-dimensional structures or in two-dimensional structures. And yeah, we're going to carry it on from there. So with that being said, let's jump into the theory. So if you guys remember, back in quiz number 13, I presented you guys this figure right here. And the key here was to show you the two different ways that we can measure deformation. We have a position function, which was labeled x, and we have a displacement function, which is labeled u. And we're able to create a relationship between the two where little x is equal to big X plus u. Now, when we're talking about strains, the key here is we're going to use the exact same diagram, except we're going to add 2 points. So as we can see, we added 2 points to these guys' heads, and from there we can create 2 vectors. So the first vector I'm going to create is called dx, where the x here is a big X, big dx. And the second vector is over on the other side, which is dx, but this time we have the small x in dx. And what we're going to do is we're going to use the relationship between these to create another vector, which is ux plus dx. And using these, we can actually formulate the following equation, where dx is equal to big dx plus the displacement gradient times big dx again. You guys do not need to know where this comes from or what it means, but all I wanted to do is show you guys where all these strain formulations come from. So when we start talking about the strain matrices, they all come from this equation here, and this equation here is derived using the following diagram. So again, you guys do not need to know this. I just wanted to include this to see, or to show you guys exactly where everything comes from. Because if we look at dx and big dx, we can see that those are the length of the vectors. And if we can tell how the length between 2 points changes, well, then we know the strain, because that's exactly what the strain is. It's the change in length over a certain distance. So when we're talking about deformation and displacement, we were given 2 gradients. The first one was the deformation gradient f, which we covered before, which is basically just a bunch of partial derivatives of that small x. Now, we covered a second one called the displacement gradient, which was basically the same formulation as the deformation gradient f, but instead of taking the partial derivatives of all those small x's, we took the partial derivatives of u instead of small x. And we were able to say, okay, well, this deformation gradient f, it was very important when we were considering deformation characteristics. Because as you guys remember, we used the determinant of f to tell us a lot of things. The first one being, is the deformation even possible? And then the second one was, is the deformation an expansion, a contraction, or even volume preservation? So we remember that the deformation gradient here was very important to us. But when we looked at the displacement gradient, that nabla u, well, we didn't really use it for anything. Sure, we calculated it, and it wasn't a problem to calculate, but we never really used it or were able to extract information from it. Well, this is where things change because as you guys will see, this nabla u, the displacement gradient, is very important when it comes to strain measures. So if we look at strain measures, remember that I showed you guys an equation in the first slide. It was a very complicated equation. I said, you guys do not need to know where this comes from or how to derive it. Well, we can simplify that equation into the following strain matrix, which is called the green strain matrix. So there's the keyword. It's the green strain matrix, which is equal to 1/2 of nabla u plus nabla u transpose plus nabla u transpose times nabla u. So as we can see, this displacement gradient appears absolutely everywhere when we're talking about strain matrices, which is why it's important and which is why we showed you guys how to calculate it so many times before. Now, a strain matrix, it's very powerful. It includes a lot of high-level math. But for us, when we're talking about structures, because remember, we're civil engineers. We don't care about absolutely everything. We care about structures. And when we think about structures and we're talking about displacements of a structure, the displacements are usually very small. If we had a structure that was experiencing, let's say, 1 meters of displacement swaying back and forth, well, it scared the shit out of you guys. No one wants a structure that goes for a lot of displacement. And because of this, we can actually simplify this equation. Because as we see is this last term here, this delta U, nabla U transpose nabla U, which is called the infinitesimal strain measure. This right here, as we'll see, is very small, is almost equal to 0 for small deformations. And this is perfect for us because, again, when we're talking about structures, we want our deformation to be small. If we had a structure or a high-rise building experiencing a lot of deflection and deformation, well, again, people wouldn't be too happy. They'd be very scared. And you guys are saying, well, Clayton, if we're talking about a 3x3 matrix, well, is it really that hard to include it? And the answer is no, of course not. We can easily calculate this. But as you guys can imagine, an actual building, an actual structure, these nabla U's, these displacement gradients are actually extremely huge. So by neglecting this term, will save us a bunch of computation time. And computation time, as you guys will figure out later, is going to be very important to us. So what we can do is we say, okay, well, our structure is going to have small deformation. So therefore, let's assume that nabla U transpose nabla U is equal to 0. Well, from here, we can create a second state strain matrix, which we call the small strain matrix. So it's equal to the same formulation, except we're neglecting that nabla U transpose nabla U. And as you guys will see when we start talking about the assignments, we're going to have two different strain measures. First is going to be the green strain measure, which uses the equation above. And the second one's going to be the small strain matrix, which we use below. So in the end, we have two strain matrices, and they're going to be used for different scenarios. Now, as you guys will see, again, the key assumption between the two is small deformation. And as you guys will see, when it comes to the examples, is sometimes this assumption of small deformation does not really work, especially when we get into rotation matrices. So that's just a little tidbit, a little surprise for later on. So now let's talk about the strain matrix. And when I mean strain matrix, I mean the small or the green strain matrix. Because as you guys will see, there's going to be some similarities between the two. And we're going to start talking about specific terms in them. So it's good to know what the terms are. So the first one is the strain matrix is a symmetric matrix. Therefore, epsilon ij is equal to epsilon ji. So if we compare the matrix on the left and the matrix on the right, we can see that epsilon 1, 2 is equal to epsilon 2, 1. So if we look at the matrix on the right, we can see that there's a lot of nice similarities, and in the end, we only have 6 unknowns. And this is for three-dimensional 3x3 matrix. And if we look, there's going to be two specific components. The black components, which are epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3, we call these the normal strains. And they are the strains in the directions of E1, E2, and E3 directions, respectively. Now, E12, E13, and E23, we call these the shear strains. So as you guys will see, if we consider a two-dimensional matrix, the only shear strain in there will be epsilon 1, 2. So if it ever talks about shear strains in two dimensions, we're going to be looking at that epsilon 1, 2. If it asks for the normal strain in the direction E2, well, then we're going to be looking at epsilon 2, 2. So as you guys will see again in the quiz, the naming scheme for these is going to be quite important, especially moving forward, because this will also come into play when we talk about stresses. So the last thing that we're going to talk about too is strains in an arbitrary direction. So remember that from the strain matrix, we can find the longitudinal strains in the directions of E1, E2, and E3 respectively. But now we say, okay, well, what happens if I want the strain in some random ass direction? Well, we use the following formula, where the strain in direction dx, so dx is just a vector. It's not a differential or anything like that. It's just a vector, is equal to dx dot the small strain matrix multiplied by dx divided by the norm of dx squared. Now let's say that we wanted the shear strain in the direction of a basis vector. And as you guys can see, we use the exact same formula, but again, those basis vectors are normalized. And if they're normalized, then the norm of a basis vector is equal to 1. So as we can see that EI squared, the norm of EI squared, that just goes away because it's 1. And we're left with EI dot E small times EI. Well, that's just equal to the partial derivative of UI with respect to XI, which is equal to nabla U II. So for instance, if I wanted the strain along the E1 axis, that's just the same as the component of my displacement gradient, 1, 1. Something like that. So hopefully this makes sense. I know it's a lot of information to swallow, and just wait until we get to the quiz. You guys are going to have to swallow a lot more. it's going to be crammed down your throats. So again, before we start the quiz, make sure you guys got your snacks, maybe take a washroom break, pour yourself a drink, because yes, this is going to be a beefy quiz, but the topic is really important. So hopefully we can explain it clearly and you guys will be nice and happy moving forward. So with that being said, let's jump into the quiz. All right, so the quiz itself is 5 questions, and unfortunately, each of the 5 questions is pretty long, except for question number 3. That one's not too bad, but yes, the rest are pretty long. We're going to be here for a while, so I hope you guys are comfy. We're just going to jump in with the first question, which says, a two-dimensional displacement function of a unit square whose centroid is situated at the origin has the form, and it gives us x, which is equal to x1, x2, and then it gives us the formulation. And with this, it says, sketch the deformed shape, calculate the small strain matrix. So I'm going to highlight that really quick because that's going to be important. The small strain matrix, because again, remember, we have 2 different strain matrices. We have the small strain and the green strain matrix. And part C says calculate the small strains along the directions of A, which is equal to the vector 1, 0, and B, which is the vector cosine 45 degrees and sine 45 degrees. So we're going to jump in by looking at the first question, which is sketch the deformed shape. So if we come down here and we look, and this is our original shape, the green one, all we have to do is take our coordinate points and substitute them into the matrix. So for instance, if I was looking at this point right here, I know that in its current state, it's 0.5, 0.5. So all I have to do is take that 0.5, 0.5, substitute it into here, and I'll get my x1 and x2 of my deformed shape. So I'm just going to erase this really quick so I know what these are. So all you guys are going to have to do is sub in the original coordinate points into this equation above, and you guys will get the deformed shapes. So I'm not going to show you guys how to do this or calculate it because you guys are experts. You guys will know how to do it. So what happens is we're going to get a deformed shape that's going to look something like this, where these two, some of the corners don't change, but the other corners do change. So this shape provides us with a very important piece of information, as you guys will see, and that's this right here, is this angle. So this angle theta, we can tell, is less than 90 degrees now. And this is going to be very important because this means that there's some shear deformation going on. So when we get our small strain matrix, what we'll expect is that there is some shear deformation. So I'm just going to erase this really quick, and I'm just going to write in the coordinate points. So when you guys calculate this, you guys should be able to calculate the coordinate points and say, okay, I got the same as Clayton. It should be right. So the coordinate points of these two corners after the deformation are 0.6, 0.6, and then negative 0.6, negative 0.6. And then the other 2 points, as you guys will see, they don't change. So in this case, we have 0.5, comma, negative 0.5. And then on the other side, we have negative 0.5, comma, 0.5. So negative 0.5, comma, 0.5. So this is very interesting how some of the points don't move, but some of the other points do move. And again, because that angle there is less than 90 degrees, we know that there's going to be some shear going on. So if we get a strain matrix now that doesn't have any shear components, we know something's going to be a little bit off. But with that being said, let's jump into it because part B says calculate that small strain matrix. So I'm going to come down here and say, okay, well, if I want the small strain matrix, I know that E small, so the small strain, is going to be equal to 1/2, and then in brackets, I know it's going to be nabla U plus nabla U transpose. So if I look at this, the only thing that I'm missing from this equation is my nabla U. And I come up here and I say, okay, well, they gave us position functions. And remember, with position functions, we can very easily find the deformation gradient F. And here's the trick. The trick is if you guys are given something like this, and actually I should have drawn a square. Let me actually switch. If you guys are given something like this, because you guys will see this a lot, especially in a midterm, because here's kind of the trick. If you guys are given something like this, and all the entries in this matrix here are constant, so they don't have x1 or x2, then that matrix there is actually our deformation gradient F. So what I could do right here is I'm just going to actually erase this. So again, if all those values are constant, which they are in this case, this matrix here will actually be equal to our deformation gradient F. So what I can do is I can come down here and say, okay, well, I'm looking for nabla U, but I already know F, and there was a relationship between F and nabla U. So the first thing I'm going to do is I'm just going to write down my deformation gradient F, which is 1.1, 0.1, 0.1, and 1.1. So again, this was just from the question. Now, if you guys wanted to and you guys don't know the trick, that's completely fine. You guys can expand out the position functions and then take the partial derivatives. But this is just a little trick to save you guys some time. So now that we have the deformation gradient f, the question becomes, okay, well, how do I find nabla u? Oh, I remember there was a nice relationship where nabla u is equal to f minus I, where I is the identity matrix. So all we have to do to f to get that nabla u is subtract 1 from all of the diagonal components. So I come down here and I say, all right, well, my nabla u is going to be f minus I, where again, we're only subtracting 1 from the diagonal components. So I'm going to write it out here. It's going to be 1.1 minus 1. The off-diagonal components have nothing. They don't change. So we're still going to have 0.1 and 0.1. But the 1.1 at the bottom, that's a diagonal component. So we're going to subtract 1 from that. So I'm just going to clean up the matrix a bit. And as you guys will see, we'll get that nabla u is equal to all 0.1s. So 1.1 minus 1, well, that's 0.1. The off diagonals, well, we're already given that those are 0.1. And finally, the other diagonal component at the bottom, 1.1 minus 1, well, again, that's just going to be 0.1. So as we can see, it's actually not too hard to find the displacement gradient nabla u. And once we have that, it's very easy to figure out the small strain matrix. So all I have to do is take E small, which is equal to 1/2 nabla u plus nabla u transpose. So I come down here, and I'll actually show it to you guys, because why not? We got nothing but time. I probably won't do this for the future questions, but it's nice to see it at least once. So we're going to have 1/2, and then in brackets, and we're going to have nabla u. That's a little bit crooked. I'm trying to make sure that my matrices look a little bit better. So the first one is just that nabla u, which is the 0.1, 0.1, 0.1, and finally, of course, 0.1. So again, nabla u is nothing too special in this case. And then we're adding this to the transpose of nabla u. And if we look at nabla u, all the entries are the exact same. So the transpose of nabla u in this case is just going to be nabla u again. So we're going to have 0.1, 0.1, 0.1, and finally 0.1. And the reason why I'm showing you guys this is because this is a very special case, as you guys will see, where if we look at the addition of this, if we take the first component, which is, my highlighter's in pink, I better change that. If we add the first component to the second component, we get 0.2. But once we factor in the 1/2 at the end, it's going to go back to 0.1. So in this particular case, since nabla u is equal to nabla u transpose, E small is actually going to be equal to nabla u, our displacement gradient, which is going to be equal to 0.1, 0.1, 0.1, 0.1. So it's actually kind of a funny question this way in that it actually works out very nicely for us. So 0.1, 0.1, 0.1. So I'm just going to finish this off here like this. So again, this is not always the case. You will not always have your nabla u equal to your small strain matrix, but in this case, it's a little bit funny that it did. And going up to above, remember we mentioned that since this angle between these two is less than 90 degrees, we expected a shear component. So E12 must not be equal to 0. And if we come down and look at our strains, well, yes, we can see that E12 is not equal to 0. And in this particular case, it's actually equal to 0.1. So that was expected, and it's kind of verified by going through and looking at the matrix. So if we come down here to the next part, we want the strain along that vector A. So I forget which part this is. I believe it's part C. Yeah, it's part C. So I'm going to try and label it so we can follow along as best we can. So the first thing that it wanted the strain along A. So I'm just going to put epsilon of A, which means the strain in the direction of A. And remember that we have a nice formula for this. So this is equal to dx dot, so again, that's the dot product. That's just not multiplication. Dot E small, which we have above, times dx, all divided by the norm. So the norm is those nice absolute bracket signs. So the norm of dx squared. And I know this formula looks confusing because it's dx. It looks like it's some sort of derivative. But remember that dx is just the vector in which we want to find the direction along. So in this case, our dx is actually equal to a, which is simply 1, 0. And what we can do is we can find the norm of dx. So this is just the norm of a, which again, I'll show you guys the calculations because it has been a little while since we discussed norms. So remember, the norm is just all of the components inside squared, then summed, and then square rooted. So it's going to be 1 squared plus 0 squared, which is just going to be equal to 1. And in this case, that's really nice that it's equal to 1 because our whole bottom term, which I'll highlight right now, all of this is going to be equal to 1, so therefore we can just neglect it. So when we come down here, we can say that E, so our epsilon, or a strain in the direction of A, is simply just going to be dx dot E small multiplied again by dx. So in this case, we have a vector dx dotted with a matrix multiplied by another vector. And that E small multiplied by dx, well, that's going to be a vector. So in the end, we're going to have a vector dot a vector, which will again give us a nice scalar value, and that scalar value will be our strain. So if we come down here, and I'm already running out of room. I thought I'd give myself enough room, but these questions are extremely, extremely beefy, so I'm going to have to maybe do a little cut edit there in the end. But if you guys see that disappear, that's why. So from here, we can say that EA is going to be equal to dx, which we know is just the vector 1, 0, and it's going to be dotted with the vector created by taking E small and multiplying that by the vector dx. And once you guys do that, you guys will find that E small times dx is equal to the vector 0.1, 0.1. And if you guys take the dot product, remember, this is going to be equal to 1 times 0.1, so I'll just write that here. So this is going to be 1 times 0.1, which is going to be 0.1, plus the second component's multiplied, so 0 times 0.1, so this will be 0. So therefore, our EA, in this case, is equal to 0.1. So this is the strain in the direction of A. And if we look up here, we remember that if we look at A here, dx, this is a basis vector EA. So this is actually the strain E11. So if we look at EA, which we got as 0.1, and we compare that to the value in our strain matrix in the direction of E1, we can see that they are the exact same, which is expected. Now, if I were to ask for the strain in the direction 0, 1, well, that's the same as the strain in the E2 direction. And in that case, I will also get 0.1 because it's given already in the matrix. So this was kind of a funny case where we were taking the strain along a basis vector and we didn't even know it. And that's why it's equal to what we had in our matrix. Now, part B, when we take the strain along B, we can see that B is not a basis vector. So then we're going to get a strain that's probably not appearing into our small strain matrix. So again, I ran out of room, so I'm just going to do a quick cut, and we'll get back. When I get back, we'll talk about the strain along B. All right, guys, welcome back. I'm sorry for the cut. Again, I just had to add a page so we weren't running into question 2 already. These questions, as you guys have seen, take up a lot of space. So now, just recapping, all we did is we found the strain along A, which in this case, A was the same as direction E1, and we got our strain to be 0.1, which was the same as component E11. Again, it was expected because that was the strain along our basis vector. But now we're going down and say, okay, well, instead of the strain along A, what is the strain along B? So again, this is going to be the same formula before, where it's going to be dx dot with E small multiplied by dx, and this will all be divided by the norm of dx squared. So the norm of dx. But in this case, our dx, which is our vector in which we want to find the strain along to, is actually equal to cosine 45. So cosine of 45, and then sine 45. So again, we can tell that this is not the same as along a basis vector. This is going to be some sort of diagonal line in the 2D plane. So we come down here and say, okay, one of the keys that I'm going to need is that norm dx. So I come down here and say, okay, well, the norm of dx is going to be equal to the square root of all those components squared. So we're going to have cosine squared of 45. And you guys will probably already see what this is equal to, but plus sine squared of 45. Finish off the square root sign here. And what you guys will see is this is nicely equal to 1. So it may not be always equal to 1, but in this case, I don't know, the quiz gods were smiling on us. And in this case, it's simplified to 1. And that's great because that means that this term below here is just equal to 1. So therefore, our strain along the vector B is going to be simply dx dot with E small times dx. And we know dx and we know E small, so all we have to do is simply sub the numbers into our calculator. So if I come down here below, I find that dx, once I simplify the sines and the cosines, this will be equal to the vector 1 over root 2. So this is just cosine of 45, and then 1 over root 2. And then this one is the sine of 45, dot, with e small times dx. And what I get for e small times dx is the vector 0.141, 0.141, and 0.141. And even though this looks really gross, where on one side we got a square root sign, and the other side we got 0.141, once we dot these together, we find that our strain along B is simply just 0.2. So just to kind of clarify, because again, some people may be lost in these calculations, this vector dx, well, that's this right here. So I'll just underline it so you guys can see exactly what this is. E small times dx, so all this put together on this side, this is the second component over here. So what I recommend for you guys is don't try and solve this in your head where e small times dx. Just put e small in your calculator and then put the vector dx in your calculator and multiply them together, and it'll give you the vector e small times dx. So after we do that, we say, okay, this is 0.2, and now this is important because if we look at the top here and compare it to our small strain matrix, we can see that the entry 0.2 doesn't appear anywhere. So this is why we need to know this formula, because there will be cases in which we're finding strains that we can't just look at our small matrix and say, okay, there's the strain right there. In this case, we actually had to do some calculations, and we found a strain that was 0.2, which was larger than any of the entries in our small strain matrix. So that is question 1. Again, as you guys can probably already figure out, it's a pretty beefy question. And luckily for us, question 2 is no different. So again, I'm going to just cut between questions. I'm trying to save as much time as possible and keep this looking neat. So let's jump to question 2. The question 2 says, find the displacement functions that would satisfy the following. And we're given 3 long ones, and these took me forever to write out, so hopefully you guys appreciate all the writing. So part A says, vectors aligned in E1 are in compression, while the shear strains and the strain 2 are equal to 0. So basically what this means, and this is kind of testing our terminology, and I'm going to switch back to pink. What this means here is it wants the strain 1,1, because remember, the strain 1,1 is the same as the strain along the direction E1, and it wants this in compression. So it wants epsilon 1,1 to be less than 0, because this is what it means for compression. Now, part B says, the vectors aligned in E2 are in tension, while the shear strain and epsilon 1,1 are 0. So in this case, it wants I can't talk, the strain shear, they all sound the same in the end. This wants the strain along E2, which is the same as epsilon 2 to be in tension. So for something in that direction to be in tension, epsilon 2 has to be greater than 0. And then finally it says E12, or I guess, epsilon 12 is positive, while all the other strain components are 0. So the key here is going to be that epsilon 1,1 is going to be equal to epsilon 2, which is going to be equal to 0. And even though it sounds easy to make those strains equal to 0, it's only one particular case in which that happens. So if we look here, what we're going to start off with to kind of figure out this question is the case in which epsilon 1,1 or epsilon 2 is equal to 0, because it appears in all 3 types of questions. So if we look at part A, it wants the case where epsilon 2 is equal to 0. If we look at part B, it wants the case where epsilon 1,1 is equal to 0. So therefore, we need to figure out this case where epsilon 1,1 or epsilon 2 is going to be equal to 0. So if we come down here and we say, okay, let's try and remember what exactly the strain matrix is. So remember that our strain matrix, which I'm going to have E small, and this could be a pretty lengthy question, but I'll try my best. Again, this is the question I was dreading the most and trying to show you guys. So remember that E small is equal to E11, E12, E12, and instead of epsilon, I'm just going to say E. It's easier for me, and it's probably easier for you guys, and E22. So remember that this is our matrix, and these are the entries that we want to try and modify. So let's try and figure out where exactly these come from. Well, remember that this is equal to 1/2 of nabla U plus nabla U transpose. And you guys may already have the entries, but it's very easy to see where exactly these come from. So if I'm looking at E11, this is going to be equal to 1/2 of nabla u 1, plus nabla u 1 transpose. So the first thing that we're going to figure out really quickly is that if we transpose nabla 1, so we're switching the two subscripts, well, it's just still going to be 1. So this is a special case in which the transpose doesn't even matter. And now if we look at this question, we can see that it's going to be 1/2 nabla u 1 plus nabla u 1. Well, that's just 2 nabla 1. And actually, I'm going to write that down here so you guys can see. Oops, sorry about that. So this right here, as we can see, this is actually just 2 nabla u. And if we multiply that by the 1/2, what we end up getting is that E11 is actually just equal to nabla u 1. And we can go through and do the exact same thing for E22. So in the end, you guys will find that E22 is just going to be equal to nabla u 2. And that's the reason why, is because we're just adding 2 together, but then we divide by 2. So it effectively cancels out in the end. The 1/2 and the transpose stuff, that'll play an important role when we talk about shear. But for here, it's not too bad at all. So remember that for this to be equal to 0, so again, I'm going to actually just highlight, we're interested in the case where these are equal to 0. So this is equal to 0. Well, if we have nabla 1 and nabla 2 is equal to 0, let's think of how that impacts f. So if I come down here and I remember, okay, well, f 1 is simply nabla u 1 plus 1. Well, therefore, in order for nabla u to be 0, f11 has to be equal to 1. And this goes the same for f22. So f22 is going to be equal to nabla u 2 plus 1. So therefore, if we want our nabla u to be equal to 0, then f22 must be equal to 1 as well. So this is going to be a very important role when we start talking about the rest of these questions, because anytime where it says E11 or E22 is equal to 0, well, that means that the entry F22 or F11 has to be equal to 1, and that's what will give us a strain of 0. So if we go up to the top here, let's look at the first one. So the vectors aligned in E11 are in compression, so therefore we want E11 less than 0, while the shear strain and E22 are 0. So if I come down here, let's look at our matrix F and try and figure out what exactly we need. All right, guys, I know I had a weird little cut in there. I started rambling, going off in tangents, and this question's a real bitch to try and explain to you guys. I'm going to be honest. So I decided, you know what? I'm rambling too much. I'm just going to throw away all the garbage I said, and we're going to start fresh, and hopefully I can try and make more sense a little bit this time. So what I just discussed above was that if we want our strain to be equal to 0 in the normal direction, so that's again in the normal direction, which would be, and I'll highlight this, E11 or E22, then we need F11 is equal to 1 if we want E11 equal to 1, or if we want E22 equal to 0, then we need F22 equal to 1. So there's going to be the first kind of key that we're going to have to realize when we're dealing with these strain matrices. So I'm going to come down here and say, okay, well, let's try and figure out what our F matrix for part A would be. So I'm going to come down here and I'm going to draw a nice square bracket for you guys. Well, I'm going to try to draw a nice square bracket if the iPad lets me, but oh, there we go. Finally got it. Third time's a charm. So we're going to come up and let's look at the conditions of part A. It says a vector aligned in E1 is in compression. So that E1 is related to F11. And we don't really know how it goes into compression. So right there, I'm going to put a question mark. I'm going to come up here and read the rest. It says, okay, while the shear strain and E22 are 0. So I'm going to come down here and, okay, for shear strain, these have to be 0 for shear strain. So I'm going to put 0, and I'm going to put 0. And for F22 to be equal to 0, or sorry, the strain along 22 to be equal to 0, we concluded above that F22 must be equal to 1. So again, this 1 here is to make sure that our strain in that direction is equal to 0. So now the question becomes, okay, what is that last question mark? Well, remember, we want the strain 1 to be in compression. Therefore, this strain right here has to be less than 0. And we concluded, okay, well, if the strain is less than 0, this means that nabla u 1 also has to be less than 0. I say, okay, well, I remember that there's a nice relationship between f and nabla u, where f is equal to nabla u plus 1. Therefore, if F11 is less than 1, nabla U will be negative, which is exactly what we want. So now nabla U is going to be a negative value. And I don't know why I put negative there. I can just put nabla U is less than 1. So this is exactly what we want. So the key here is we need to find a value of F11 that's less than 1. Now, we're going to see that it sounds easy, but it's actually quite difficult because there's a trick that we're going to have to keep in mind. So I'm going to come down here and say, okay, well, if I look at this, I can pick a variety of options. So what I'm going to do, I'm going to change color. Actually, let's go with something really fancy. Let's go lime green. So let's say that I pick F11 is equal to -6. And if I look above, -6 is less than 1. So therefore, I'm meeting my criteria. But let's take the determinant of f now that we say that this is equal to -6. So the determinant of f, in this case, using -6 as F11, is going to be -6 times 1 and then plus 0. So in the end, we get the determinant of f is equal to -6. And we remember that if the determinant of f is less than 0, or any negative value, which is what we have, this deformation right here is actually not possible. So therefore, there is kind of a second limit on F11 in order to ensure that our deformation is possible. And if we look up at this equation, the determinant of f here, the only way that the determinant of f will be greater than 0 is if F11 is greater than 0. So I'm just going to make a note here where for the determinant of f to be greater than 0, we need F11 to be greater than 0. So therefore, now we're given kind of two things that we need to look at. The first is what we said above, where F11 has to be less than 1. But now we're given the second condition that F11 also has to be greater than 0. So therefore, I can come down here and say, okay, well, I can say that my F matrix now is going to be equal to, I'll just put this right here, and I'll put alpha, and we're going to define what alpha is, and then 0, 0, and 1. And now we have to state our limits on alpha, where we know that alpha has to be greater than 0, but less than 1. So I can say alpha has to be greater than 0, but less than 1. And remember, right now we just have the deformation gradient. We don't have our position functions, which is what the question wants. So if I were to come through here, I remember that, okay, well, these are basically just the partial derivatives. So if I were to look at the actual position functions, I just integrate each one of these. And you're saying, oh, integration, wait, integration, shit, I don't want to do integration. Well, don't worry, if we look at these values, they're just constants. So integrating them is just as simple as putting an x at the end of them. So if I were to look at x1, it's going to be alpha x1 plus 0 x2. So I'm just putting kind of the x's on the end because that's all we need to do for the integration. So in the end, we see that x1 is equal to alpha x1. And I can do the same for the bottom one. So we see that x2 is equal to 0x1 plus 1 x2. So therefore, x2 is simply just going to be x2. So from here, we can see, okay, well, now I have my position function. So as my answer, I can state that x is going to be equal to, and I'll just draw a nice bracket. It's going to be equal to alpha x1 and then x2 at the bottom. And then we're going to have to state our limits on alpha because alpha can't be anything. Remember, alpha has to be greater than 0 and less than 1. So if this is the case right here, this position function, this will give us 0 shear strain. It'll give us 0 strain in the 2-2 or E2 direction. And it'll give us a compressive strain in the E1 direction. So this is going to be my answer for part A. So I'm going to highlight it right here. Just make it kind of nice and fancy. So as we move on to part B, as you guys will see, part B is actually very similar to part A. So I'm going to come down here and I'm going to start by talking about my deformation gradient. So we know that f is going to be equal to a bunch of numbers, and we're going to look at the question's criteria for these numbers. So looking at part B, it says vectors aligned in the E2 direction are in tension. So E2 now is what we're kind of trying to figure out. So this bottom one right here will be the question mark, and it also says that the shear strain and the strain in E1 are equal to 0. So we come down here, and remember, for shear strain equal to 0, we just put zeros. And then for E1, the strain along E1 to be equal to 0, we need F11 is equal to 1. So it's the same situation we had above, except now the problem becomes, okay, well, what is that bottom entry? So remember that if we want this to be in tension, so E22 to be in tension, this has to be greater than 0. Well, we remember that E22 is simply equal to the displacement gradient U22. So therefore, this has to be greater than 0. And we can go a step further and say, okay, well, in order for that to happen, we can use our relationship between the displacement gradient and F, and we can conclude from this that F22, I just about put 1, F22 must be greater than 1. So this is perfect because unlike before, we'll see that any F greater than 1 will work in this because let's say that I pick F22 is equal to 6. So F22 is equal to 6. So this, again, above 1. Well, my determinant of F, if I pick this, determinant of F is equal to 6, which is greater than 0. So as we can see, no matter what we pick in this case, we'll always get physically possible motion because F22 will always be a positive number. So therefore, in this case, again, I'm just integrating everything. In the end, what I'll find is that x1 is going to be equal to 1 times x1 plus 0 times x2, where x2 now is going to be equal to 0 x1, and then we're going to add on a plus, and I'm going to put alpha again, alpha x2. Where did I get alpha from? Well, that's above from up here where I had the question mark. I'm just erasing that question mark and putting alpha instead. So from here, we can easily see that x now is actually going to be equal to, and I'm just going to put the nice brackets, x1 and x2. So x1 right here, we just got x1. And then at the bottom, we have alpha x2. And again, we're going to have to state our limits for alpha. So in this case, alpha, all it has to do is be greater than 1. And that's it. If we have alpha is greater than 1, then our strain along the direction E2 will be in tension. All right, so part C is the last part. It says E12 is positive, so our shear strain is positive, while all other strain components are equal to 0. So we're just kind of wrapping this up nicely. I'm going to come down, and you know what? Let's just draw a line so we really know where the difference between the questions are. So this is part C. And let's look at our deformation gradient F. It says that all other strains besides the shear strain are equal to 0. So we know that if we want the strain along E1 to be 0, then F11 has to be 1. We know that if we want the strain along the direction E2 is equal to 0, then we know that F22 must be equal to 1. So now the question becomes, all right, so what are going to be these shear components, which will put alpha and beta in here? So let's try and figure out how this shear is positive. If the shear is positive, then E12 must be greater than 0. Makes sense. All right, well, to get a positive shear, I just need a positive value in the shear strain. Well, if we look at what E12 is equal to, and I'm going to come down here because this one's going to get a little bit more complex. E12 is equal to 1/2, I'm going to put in brackets, nabla U12 plus nabla U21. So again, the displacement gradient, nabla U, doesn't always have to be symmetric. Therefore, it doesn't simplify as nicely as the the normal components 1, 1 or 2, 2. So if we look at this case and we say that, okay, well, this has to be greater than 0. Well, if we look at this, then what we conclude is that nabla U1 plus nabla U21 just has to be greater or equal to 0. But again, we're not concerned too much about nabla. We want what this will be in terms of our deformation gradient F. So as you guys remember, in order to go from the displacement gradient nabla U to deformation gradient F, we use the following relationship, where nabla U is equal to F minus I. But here's where we have to kind of look at something and go, okay, well, minus I. Well, I only affects the diagonal components, so that'd be the components 1, 1, 2, 2, or 3, 3. It doesn't impact the off-diagonal components, which in this case would be 1, 2, and 2, 1. Therefore, we can say that all we need to do to ensure that we have a positive shear strain is F12 plus F21 is greater than 0. So I come down here and I can just go, okay, well, my deformation gradient F, which is equal to, I'll just come down here, finish off the brackets, which was equal to 1, alpha, beta, and 1. I'll just finish this off here at the end. All I have to do to make sure that this is equal to a positive shear strain is that alpha plus beta, so alpha plus beta is greater than 0. And if I have it's greater than 0, it'll guarantee me a positive shear strain. So what does this look like in terms of x1 and x2? Well, again, all we have to do is integrate. So x1 is going to be just simply x1 plus alpha x2. And x2 is going to be beta x1. So again, I'm just integrating. And when we're integrating the constants, all we have to do is just tack on an x onto the end. Plus 1x2, which is just x2. So therefore, we can say that x is going to be equal to, and I'll put my nice bracket here, and I don't know why it's not correcting. It just doesn't like me today. So this will be equal to x1 plus alpha x2, and then we got beta 1, beta x1 plus x2. And this right here will give me a positive shear strain, while the strains along the E1 and E2 direction are equal to 0. So again, the key here is that alpha plus beta has to be greater than 0. And that concludes question number 2. So question 3 is the simplest question of them all, which is great, because if you guys need to take a break, grab another drink, something like that, well, question number 3 is perfect for it because it's nice and short. However, the problem with question 3 is even though it's the shortest question, it's the one that'll create many questions for you guys saying, wait, this doesn't really make sense physically. And yes, as you guys will see in continuum mechanics, there are cases where the math just looks really weird and doesn't make any physical sense. And as you guys will see in question 3, this is one of those cases. So question 3 simply says, calculate the small strains associated with the rigid body rotation of 11.6 degrees. So what does it mean by that? It means that we have our position function here, right here, this matrix here. This is our rotation matrix Q. So all we need to do is figure out the small strain matrix for this question. So we know that, again, if we're given a Q here, a matrix that's just full of constant numbers, we know that Q is actually going to be equal to F. So I can come down here and say, okay, well, this is great. I already know that my F is going to be the 0.98. 0.98. It's going to be 0.2. It's going to be negative 0.2. And finally, on the other side, we have 0.98 yet again. So I'm just going to clean up this matrix, make it look a little bit prettier. You guys deserve nice looking matrices, so hopefully I can give you guys that. And remember, if we're trying to find the small strain matrix, we utilize the following formula. So E small is going to be equal to 1/2 of nabla U plus nabla U transpose. So again, who cares if we have F, we need nabla U. Well, remember that we can easily find nabla U because nabla U is just going to be equal to F minus I. F minus I. So I come down here and I say, okay, well, my nabla U, my displacement gradient, is going to be equal to 0.98. And just try and make this a little bit straighter. Again, you guys deserve nice looking matrices. So it's going to be 0.98 minus 1. Below that, it's just going to be 0.2 because we're only subtracting 1 from the diagonal entries. We have 0.2 and 0.98 again minus 1. So 0.98 minus 1. Clean up the matrix a little bit. I see that my one bracket's a little bit crooked. Hopefully you guys forgive me for that. All right, we come down again. And once we do all the mental math on this, what we'll get is negative 0.02, negative 0.2, 0.2, and negative 0.02. So a lot of 2's as we can see in this matrix here. So there, now we have nabla U. So from here, all we have to do is put this into our calculator and substitute it into the small strain formula above. So if I go E small now, and I throw everything in, which is basically just my nabla U, I can find that my small strain matrix is going to be equal to this. Negative 0.02, 0, 0, and negative 0.02. So I'm just going to clean this up at the end, and this is it. This is all the question asks for. And you're saying, Clayton, why did we get such an easy question? These questions have been really beefy. How come this one's pretty nice? Well, the goal of this one is to show you guys that sometimes we have to be careful of what we assume. Remember, all we're doing to this object is just a rigid body rotation. We're not stretching it, we're not compressing it, anything like that. So theoretically, all of the strain should be 0. Because again, I'm not compressing it, I'm not stretching it or anything like that. But if we look at our small strain matrix, we're actually given some strains along the two normal directions, which is technically wrong. Because remember, these should all be 0. So you're going to say, Clayton, where did these come from? Well, this actually comes from the fact that we're using the small strain matrix instead of the green strain matrix. So remember that the green strain matrix has one extra term tacked onto it. So this would be plus nabla u transpose nabla u. And this right here would be a correction factor that would make sure that all of these would be equal to 0. But again, we're assuming small deformations. And when assuming small deformations, we just use this part right here. So this goes to show that sometimes we can't always assume small deformations because we're going to start getting strains in our calculations that should not be there. They should not exist. So this was question 3. It's not too bad. And again, it's just to show you that if we use a small strain matrix for a rotation, it's going to give us strains that technically don't exist. So now I'm going to cut to question 4. I will see you guys in question 4. So question 4 says the following displacement function is accompanied by a shear strain. Find an orientation for the coordinate system where the shear strains are 0. So if we look, we're given two position functions, small x1 and small x2, and from there we can find the strain matrix. However, it wants us to find an orientation in which the shear strains are 0. So that means that entry E12 in our strain matrix is equal to 0. And as you guys may have guessed, well, how does that happen? Well, that means it must be a diagonal matrix. How do we diagonalize the symmetric matrix? Well, that goes back to eigenvalues and eigenvectors. So the first thing that we're going to want to do, though, before we jump into it too much, is we're going to want to find our strain matrix. Because again, that's the one we're going to want to diagonalize. And if we don't have the strain matrix, well, we won't know exactly what to diagonalize. So we're going to come down here and say, okay, well, I'm given two position functions. And remember, using position functions, I can find the deformation gradient f. Because this is simply going to be the partial derivative of x1 with respect to big X1, and so on and so on. So if I look at the first equation right here, which will give us the first row of our deformation gradient f, the first thing I want to do is take the partial derivative of this with respect to big X1. So I just go through the equation and I see, okay, well, I got 0.8 big X1. Well, that will change to just 0.8. And then my second entry is plus 0.1 x2. Now, if I take the partial derivative of x2 with respect to x1, it's just going to be 0, so I'm just going to leave it be. Now, if I move on to the second entry, I'm still looking at small x1, but now I'm taking the partial derivative with respect to big X2. So if I look at the first entry, which is 0.8 x1, well, if I take that derivative with respect to x2, that's just going to be 0. But when I get to the second entry, which is 0.1 x2, and I take the derivative of that with respect to x2, I get an entry of 0.1. So that's how we get the first row of our displacement or our deformation gradient f. So now if we look at the second one, we're going to get that from the small x2. So again, I'm just going to go through and take the partial derivative with respect to big X1. So I see that the first entry is 0.1 x1. Well, I take the derivative of that, I'm going to get 0.1. And again, just like before, the second term is x2. So if I take the partial derivative of x2 with respect to x1, it's just going to be 0. So I'm saying, okay, that's good. Now I'm going to move on and take the partial derivative of this with respect to x2. And I can see that that's just going to be simply 0.9 in the end. So this is going to be kind of the tricky part, because if we don't get this first part right, then the rest, of course, is going to be wrong. So now that we have our deformation gradient f, we realize, okay, well, this is all great and fancy. But remember, for the strain matrix, we want the displacement gradient nabla u. So what we're going to do is we're going to say, all right, well, we remember that nabla u is simply just going to be f, our deformation gradient, which we found just by the side there, minus I. So I come down here and I'll say, okay, well, nabla u in this case is just going to be f minus I. So I'm just subtracting 1 from all of those diagonal entries. So we're going to have 0.8. That's a go minus 1. We're left with negative 0.2. The off-diagonal entries, which are the 0.1 and 0.1, those don't change. So we're just left with 0.1 and 0.1. But the entry 2, 2, that 0.9, that is a diagonal entry, so we're going to subtract 1 from that. So we got 0.9 minus 1. We're left with negative 0.1. So I'm going to come down here, and I'm just going to finish the brackets. And now we have our displacement gradient, nabla-u. So when we're trying to find the strain matrix, this is nice and easy. So E small, so again, we're talking about the small strain matrix. This is just simply 1/2 of nabla-u, which we know above, plus nabla-u transpose. And again, that's easy because we have nabla-u above. All you guys are going to have to do is throw this into your calculator and we'll easily get values. So if we throw that into our calculator after we define nabla-u, we're going to get the matrix as follows. So I'm just going to finish up those brackets. And what we get is negative 0.2, 0.1, 0.1, and negative 0.1. So if we look here, this is actually kind of funny because this is the same as our nabla-u, and we had this in a couple questions before. So one of the questions I'm going to ask you guys to really think about is, what scenario has to happen in that nabla-u is equal to our small strain matrix? And kind of hints I'm going to give you guys is just look at this. And I guess this isn't a quiz, so I'm not going to really tell you, but the key here is that nabla-u is already symmetric. Remember that nabla-u doesn't have to be a symmetric matrix, but it just so happens that in this case, it is symmetric. And that's the symmetry of the matrix allows for it to result in the small strain matrix just right off the bat. So if you guys remember that little trick, it could save you some time on a midterm. So again, if we look at this right here, we have our small strain matrix, and in its current state, it actually has some shear strain. So there's a 0.1 shear strain in this matrix. But the question wants us, what is the coordinate system in which that shear strain disappears? So that shear strain is going to be equal to 0. Well, again, as you guys may have guessed, we're going to have to find the eigenvalues and eigenvectors of this. So in order to find the eigenvalues and eigenvectors, remember, eigenvalues, we solve the equation, the determinant, in this case, our matrix would be the epsilon. I'm not going to write small, just going to save some time because you guys already know what I'm referring to. So epsilon minus lambda I, where I is those nice eigenvalues that we're going to want. And again, this matrix must be equal to 0. So if I were to expand out the determinants, I'm going to get something like this. So the determinants, again, is those kind of absolute value looking signs. And we're going to get negative 0.2 minus lambda. And then the off-diagonal components stay the same. So it's going to be 0.1, 0.1. And then the bottom, we got negative 0.1 minus lambda. So let's bring this down like this. And again, this is all equal to 0. So we can expand this out a little bit further because we know how to take a determinant of a 2 by 2 matrix. So we got negative 0.2 minus lambda multiplied by negative 0.1 minus lambda, and then minus 0.1 multiplied by 0.1, 0.1, and then 0.1. And of course, this is equal to 0. So from here, we can see that we're going to have a quadratic equation. There's going to be 2 roots, and those 2 roots will be our eigenvalues, lambda. So if we come down here, we can say, okay, I solved this, and let's be honest, you guys are going to use Mathematica or something, or even your calculator. A calculator is a great way to solve one of these two. We're going to find that our lambda is equal to negative 0.262, so there's going to be 2 values. This is the first one, and we got negative 0.038. So we have 2 eigenvalues in this system, and what these are actually called are our principal strains. So I'm going to just write this down, principal strains. I'll show you guys exactly what they mean, principal strains. I'll show you guys exactly what this means moving forward because these are actually going to be very important. So with these, we can also find eigenvectors according to these. And you guys already know how to find eigenvectors, so I'm not going to really go through and waste your guys' time. So what we're going to find is there's going to be 2 eigenvectors. And I'll just write right here eigenvectors so you guys know exactly what I'm talking about. Eigenvectors. So I get the first one, which I'm going to label as P, is equal to, and I'll just draw kind of my nice little vector brackets. Again, you guys deserve nice brackets. Don't let anyone tell you that you guys don't deserve nice brackets. So I get 0.851, and then negative 0.526, negative 0.526. So I'll end my bracket there. So this is going to be the first eigenvector. And I get the second one, which is equal to R. Or I just put it's equal to R. You guys can really put it's equal to whatever variable you want to call it. And I get this one is equal to 0.526 and then 0.851. And as you guys will see, there's going to be some sort of relationship between these two eigenvectors, and it's going to be quite interesting to see what happens. So now that I found these, I have my principal strains and I have my eigenvectors. And why was this important? Well, remember, to get these principal strains, that matrix, what I'm going to come down here, I'm going to say E prime, which E prime is that diagonal matrix, is going to be equal to Q times E, and this is our original matrix E, times Q transpose. And remember, in order to make that E prime diagonal full of the principal strains, our Q has to consist of those eigenvectors. So Q is going to be equal to P1 and P2 as the first row. So I'm just going to finish drawing the brackets. It's going to be P1 and P2. So P1, of course, is 0.851, and P2 is negative 0.526. I come down and say, okay, well, the second row of Q is going to be my second eigenvector, which is 0.526 and then 0.851. And you guys are going to look at this and say, wait a second, this looks very familiar. And as you guys will see, this is actually a rotation matrix. And if I were to figure out the value here, we can find out that theta in this rotation matrix is actually 31.7 degrees. And this is if we were to rotate the shape counterclockwise 31.7 degrees. And our matrix that we get if we transform it by this, E prime, is going to be equal to just our two eigenvalues, which were, where are they? I'll come up here, the negative 0.262. So negative 0.262. And then again, the shear are 0 because these are a diagonal matrix. And then the last one is negative 0.038. So negative 0.038. I come down here just like that. And I say, okay, well, this is very interesting. And you're going to say, Clayton, what exactly is happening here? So let's go down here and let's draw what exactly is happening. So let's say that we have a nice square. Nice, it makes it perfect. And I apply that position function. Well, this position function will change in sort of a shear type way. So remember that before when we had shear, it would kind of make something look like this. And again, this is not exact or anything like that. Oh, let me just try and make it a little bit nicer. So this is not exactly what the position function would do. But as you guys can see, there's definitely a shear type motion because the angles of this square after the transformation are no longer squared. This is less than 90 degrees now. So I'm just going to erase this. But what happens is this, is let's say that instead we rotate our square before we apply the coordinate transformation matrix, before we apply the position function. So in this case, I take my square, I rotate it 31.7 degrees, and now after I apply my position function, now when I look at the deformation, it's actually just going to, it's actually, let's see if I can draw it nicer. As we can see, there's no shear. It's going to look something like this. So notice how the square kind of retains its shape. It's just being stretched. It's not being sheared anymore. So this is why it's so important, and this is why we talk about principal strains, because this is going to have the two principal strains, which basically pulls it in those two normal directions. So hopefully this makes sense in which we find the eigenvalues and eigenvectors. So again, the coordinate transformation matrix that we'd want to diagonalize it is going to be Q, which are just the eigenvectors, and this is going to result in a strain matrix where it just has normal components. So this would be E11 and E22. Well, the shear component E12 is equal to 0. So again, kind of a long question, brutal question. I'm getting tired. I'm sure you guys are getting tired, but bear with me. One question left, and that is question number 5. The question 5, to end off the note, is another beefy question, and it says compare the small strain matrix and the green strain matrix for the two rigid body rotations. So if we look at part A and part B, they're both just a rigid body rotation. The only difference is the amount we're rotating it by. So it's clear to see in part A, we're rotating by 11.6 degrees, while in part B, we're going almost triple that with 30 degrees. So we're going to come down here and say, okay, well, let's start off with part A. So the first trick to realize is, remember, if this matrix in front of the x1 and x2 is all constant values, which in this case it is, then this matrix Q is actually equal to our deformation gradient F. So I can come down here and say, okay, well, F is going to be equal to, and I'll just draw my nice brackets, because again, you guys need nice brackets. And F, of course, is equal to 0.97. And I know that in the quiz, it's using the approximations, but I'm going to use actual numbers. So we got 9796 at the top. We got negative 0.2011. And then, of course, it's going to be kind of the same on the other side. We got 0.2011 and 0.9796. So I'll just put the nice square bracket here. So this is what it would actually be equal to. Again, the quiz gives an approximation, but I'm using the actual real values. So from here, we can come down and say, okay, well, I remember, because you've told me a million times this quiz, that our displacement gradient nabla u can actually be found by taking F minus I. So all we're going to do is subtract 1 from all of those diagonal entries. So if I come down here and say, okay, the 0.9796, that's a diagonal entry, so we're going to subtract 1 from that, and we get negative 0.0204, and this will be the same over here, because again, on the other diagonal entry, we're taking 0.9796 minus 1, and we'll get negative 0.0204. And then the off-diagonal entries, we don't subtract anything from. They remain the same. So we're given 0.2011 and 0.2011 with the one in the corner here being negative. So I'm just going to finish off this. So now we have our displacement gradient nabla u. And again, this is the hard part. Once we find the displacement gradient nabla u, then finding out the strain matrices are actually quite simple, because we just store nabla u in our calculator and we use our calculator to easily find all the matrices. So if we start off with the small strain matrix, we know that this is going to be equal to 1/2 of nabla u plus nabla u transpose. So nabla u transpose. And if I substitute all this into the calculator, I'm going to get something as such, where I have negative 0.02, we have 0, negative 0.02, and 0. So again, we kind of touched on this in question 3, where when we're doing a rigid body rotation and we look at the small strain matrix, it actually gives us an answer that isn't, well, it doesn't physically make sense, because again, we're just rotating this. We're not actually compressing it or anything like that. So the fact that we end up with strains in the normal direction, so the negative 0.02 in both of those normal directions, tells us that there's a problem. And for those of you who are saying, well, 0.02, that's a small number. That doesn't really mean anything. It can't be that large. Well, that would actually crush concrete. Well, actually, it wouldn't crush concrete. Well, no, it would crush concrete. Well, that 0.02 would actually crush concrete. So if we look at concrete, concrete actually crushes at a strain at 0.0035. So this is almost 6 times higher than the crushing strain of concrete, which is incredible. And this is where we tell things don't really make sense, because if I take a concrete cylinder and simply just turn it, it's not going to explode on me. Well, at least I hope not. That'd be some very unstable concrete. So this is where we can tell, okay, well, there's going to be something a little bit funky going on. So the second part says, well, let's calculate, oops, and I'm using the wrong color, of course. Let's calculate the green strain matrix. So epsilon green, which is equal to 1/2 nabla u plus nabla u transpose. So again, this was exactly what we had before, except we're tacking on a term which is nabla u transpose nabla u. So the calculation of it for you guys isn't bad, because again, we're just using this in our calculator. We define nabla u, or even in Mathematica, I guess, and we just add on that little extra term. And when we substitute everything into here, we'll find that this strain matrix, by including that extra term at the end, will be 0, 0, 0, 0, which is exactly what we want it to be, because this is what physically makes sense. If we're just rotating something, there shouldn't be any strains to it. So this turns into the question of, okay, why did we use the small strain matrix? Well, again, we use it because we want to limit our computation time by assuming some of the variables are equal to 0. And in this case, what we did is we assumed that this little term at the end here, the nabla u transpose nabla u, is approximately equal to 0 for small deformations. Now, if you think about a rotation, of 11.6 degrees. That's pretty noticeable. If your floor suddenly rotated by 11 degrees, that's pretty noticeable. You'll definitely notice it. So therefore, this assumption doesn't really hold true when it comes to rigid body rotation. So now we're going to come back up and say, okay, well, we did the case of 11.6 degrees. What happens if we do the case of 30 degrees? So I'm going to come down here and we're going to do the same steps as before. So again, if we come up here, we can easily see that since this matrix in front here, it's just a bunch of constant values, then our transformation matrix Q is going to be equal to F. So I come down here and say, okay, well, F, which is my deformation gradient, is going to be equal to, and let's do the brackets really quick. It's going to be equal to cosine of 30. And yes, I'm getting a little bit lazier. As you guys can tell, I'm not even finding the decimal numbers. This quiz was a pretty long quiz. I hope that you guys are doing well. I know that after this quiz, you guys will be ready for a nap or something like that. We have sine 30 and we have negative sine 30. Almost done, guys, I promise. I apologize for the length of this quiz. I was just as scared when I saw it too. And like, oh my gosh, I got to do a video for that. Oh, they're going to be so bored and they're all going to hate me, but hopefully you guys are sticking with me. All right, so now that we have F, we can easily find that our nabla U is going to be equal to F minus I. So again, this is just using the exact same procedure that we did before. So, oops, I'm just going to come back. So again, all we're doing is subtracting 1 from the diagonal components. So we're going to have cosine of 30 minus 1. Oh, down here, we're going to have cosine of 30 minus 1. And then the signs stay the same because they're not diagonal components. So we're going to have sine of 30 at the top here. And we're going to have negative sine of 30 in the bottom corner. Let's go negative sine of 30. I'm going to finish off the brackets. I'm pretty impressed with my bracket skills. I was able to stick with it. I know in quiz 13, I got pretty sloppy towards the end because I was getting a little bit tired of drawing brackets. So again, if we look at our nabla U, even though I have it in terms of sines and cosines, those are really just numbers. So all I have to do is substitute it into my calculator, and then from there I can easily calculate my two strain matrices. So we're going to go E small, so the small strain matrix, which again is just going to be 1/2 of nabla U plus nabla U transpose. And when we throw all this in, what we're going to do is we're going to find the following. So I'm just going to finish off the brackets really quick. What I find is that it's equal to negative 0.13, negative 0.13, and then 0 and 0 on the off diagonals. So the reason why we made you guys check two different rotations is because we have to look at the amount of rotation. So if we look at part A compared to part B we're rotating it almost 3 times as much. And if we compare the strain that we got for the first one, which was negative 0.02, and compare it to the strain that we got from the second rotation, negative 0.13, we can see that this is when the formula really kind of goes apeshit and starts predicting strains that are huge. This strain right here, the 0.13, this would yield and probably almost break your steel. So again, you guys can see that this is why the small strain matrix is not a very good measure when it comes to rigid body rotation, because this is saying if I have a piece of steel and all I do is rotate it, it means that it fractures in half. And of course, that's not going to happen. There's going to be no strain at all. So the fact that we're getting such large strains here is a big sign that, yeah, the small strain matrix, it's great when we're talking about small displacements, but when we start talking about rigid body rotations, not the best to use. What do we use? Well, that'd be the green strain matrix. So if I were to find the green strain matrix again, so epsilon green, which is equal to 1/2, and then it's going to be nabla U plus nabla U transpose. So again, the same as the small strain matrix. The only thing we're adding on is a nabla U transpose nabla U to the very end of it. And we do all the substitutions into our calculator and we find out what it's equal to. Well, unsurprisingly, this is equal to 0, 0, 0, and 0, which is exactly what we expect for a rigid body rotation. Because again, we're not deforming the object at all. We're just rotating it. So again, if we were to look at the math right from the very beginning, the green strain matrix is the actual formulation. This is the actual formulation. This is why it's correct in rigid body rotation. The small strain matrix is just an easier matrix we use in the assumption that there's very small deformation. And again, when we're talking about civil structures, this is most often the case, which is why the small strain matrix is a very valid option to use most of the time. Reason why I say most of the time is, well, as you guys can see, when we're talking about rigid body rotation, it kind of goes to shit. So with that being said, the quiz is finally done. So if you guys made it to the end here, give yourselves a pat on the back, give yourselves a nice reward, order takeout or something, and celebrate, because my goodness, this was a long quiz, and I apologize for making you guys sit through it. Hopefully it wasn't too bad. I really hope it wasn't too bad. And hopefully I shed some light on the small and green strain matrix. It's a very important topic, and it's a topic that you guys will see kind of rear its head in when we talk about stresses and stuff like that. So thank you guys so much for listening. Again, this was a long quiz. You guys deserve a reward. Go reward yourself with something nice. Give yourselves a nice treat. So I'm going to thank you one more time. Thanks again for watching this video. I will see you guys in quiz number 16.